With that, I'm now going to be handing over the presentation to my colleague Andrew Dawson, where he's going to be presenting some video presentations featuring the Razor Plus digitizer series in operation in a ultrasonic type application scenario. So Andrew, I'm going to hand over the presenter status to you.
Sure. Right on. Okay. Entire screen. Whoops. Okay. Good afternoon. Just a little background. Although I did my doctorate on low temperature physics, I worked for several years in ultrasonics, research on ultrasonics. And indeed, although the gauge card finds itself in a wide variety of applications because it's able to capture high-speed signals of any nature, the gauge card can capture signals from any different sort of probe. So it finds itself, as I say, in a wide variety of applications. Notwithstanding that fact, I would say ultrasonics has always been gauge's bread and butter, with between a quarter and a half of all gauge applications being one sort of ultrasonics or another. The main division, I would say, is between material ultrasonics or non-destructive testing, a type of non-destructive testing, and medical ultrasonics, which is, as the name implies, done on patients and so forth. We may have seen our children on ultrasonic images inside the womb and so forth. So I'll be presenting some measurements on a gauge Razor Plus, and most of them will be within the context of ultrasonics measurements. So I did a number of measurements here in our gauge lab with a bunch of instruments, and really highlighting the gauge Razor Plus CompuScope 50214, which is a 2-channel, 14-bit, 500 megasample per second digitizer. You can see it here installed in a PC. It's a half-length card, so there's plenty of space there. And then if we look at the card from the back end, it's got SMA input connectors. You can see a signal connected up to channel 1, and then there's the auxiliary connections at the bottom, trigger in and out, clock in and out, some of which we'll be discussing. So as an overview of an ultrasonic system, here's really a generic ultrasonic system. So the heart of it is this box with the X here. That's the ultrasonic transducer, which when excited with a very short pulse that's high voltage, usually up to around 300 volts and so forth, it emits a ping of ultrasound here. We can see this pulse in water. In this case, we're using water as a buffer medium between the ultrasonic transducer and the slab of metal that serves as a sample. When the transducer is excited, it emits a ping of an ultrasonic pulse that travels towards the sample. At the same time, out the back of the pulsar receiver, we have an output signal. I should say that we're operating this transducer in reflection mode. So it's responsible for both emitting the ultrasonic ping, but also receiving echoes coming back, much as you would yell at a mountain, for example, hello, and listen for the echoes coming back. And indeed, by counting the delay between the time you said hello and you heard the echoes back, knowing the speed of sound, you could actually work out how far that mountain was away. Out the back of the ultrasonic pulsar receiver, though, they output a nice low voltage version of the ultrasonic signal, usually between 0 and 1 volt, plus or minus 1 volt. And then there's a trigger out, which creates, you can see here, a trigger pulse, a very sharp pulse that occurs at the time of the ultrasonic excitation, which you can see here on the signal, which saturates the input. We call it the Big Bang in the business. And so the ultrasonic pulse and the accompanying trigger pulse serve as a sort of starter pistol, okay, in the race of ultrasonic race, if you will. All echoes come after the ultrasonic, the external trigger. And in this particular case, we typically aren't interested in pre-trigger data because all the signals of interest occur after the excitation. But the gauge card is fully equipped to acquire pre-trigger data in that eventuality. So after emission of the ultrasonic pulse, it travels towards the sample over here, and you can see you get a reflection from the front wall of the sample that we see here in the ultrasonic signal, this big echo here. But not all the ultrasound bounces off the front wall. Some of it enters into the sample, travels to the back wall, and then bounces off. So it makes a round trip through the sample, and we get this back wall echo here. In fact, the sound bounces back and forth, so you get echoes reverberating with an equal delta T here until they die out. So the big measurement you often do in ultrasonics is this measurement of delta T between the front and back wall echo, and knowing the extra distance that the back wall echo has traveled, which is twice the thickness because it went there and back, you can actually measure the ultrasonic velocity in this slab of metal. And if the metal were non-uniform in some way, parts of it might be stiffer and mushier. The speed of sound tends to depend on the stiffness of the material. So mushier areas would give a slower speed of sound, and you'd be able to characterize the material that way. Alternately, you could look at the amplitude of the reflected echo. That would give you an idea of the absorption of the ultrasound. So you might, in a particularly attenuating material, be able to characterize it by the attenuation. Alternately, if the material was uniform, of like a steel slab, you could use the value of delta T to measure the thickness variation. So often this is done inside big reservoir containers that they store oil or water in. They're embedded in the ground. You can't get to the back wall because it's all buried. So what you do is you introduce ultrasound from the inside and listen to the echoes, see how thick the reservoir is, and if there's been any corrosion that might lead to a leak eventually. They do similar things on submarines. Inside of a submarine is all covered with dials and valves and so forth. So you can go over the outside of the submarine and listen for echoes to see if there's any weak spots, any thin areas in the submarine that we should look at afterward. So far I've only talked about the front and back wall echo, but of course any cracks which might occur in the middle of the slab would also reflect echoes, and those echoes can be arbitrarily small depending on how small the crack is. So looking at this ultrasonic signal, we can see that the area between the front and back wall echo is clean of any echo. So that tells us, to the extent that we can detect these echoes, that there's no cracks in this material. So this, again, sort of gives you an overview of ultrasonic NDT materials ultrasound and how you can measure thickness, material properties, and crack presence with one non-destructive measurement. So it's kind of nice because interpreting it is relatively straightforward. You don't need any fancy Fourier transforms or anything like that. I should add that this system could be replaced quite easily with any number of other reflectometry type applications. I could replace the ultrasonic pulse receiver with a pulsed laser, and then I might have a LiDAR system where I bounce laser pulses off of clouds or objects for surveying, measure the delay to work out the position of those objects. This could be a radar dish on an airplane where I'm emitting radar pulses, listening for echoes back from other planes. They even do things like in fact, I had trouble with my cable, and they brought a reflectometer box up doing the same thing, bounce echoes, and found out that there was a break in the cable because it reflected voltage waves. So as I say, although it's just ultrasound, there's a lot of elements that are common to a lot of other measurements. Here's a picture of our very old ultrasonic pulsar receiver from Panametrics. I believe the company was bought by Kramer about 20 years ago. It's really one of the lowest end models. You'll see it's kind of broken in a way that we're actually going to use to illustrate some principles. Here you can see we've got the pulsar receiver set in reflection mode. We've chosen to emit a low energy pulse. We've got over here on the left the PRF. So that's the pulse repeat frequency. So typically in ultrasonics, you're sending an excitation, listening to the echoes, but you're not just doing that once. You're doing that over and over and over again, in between which you might be moving your ultrasonic transducer across a sample, maybe in a two-dimensional grid, so that you can actually get an image of the material. So you could imagine going over a material the way you would mow a lawn in order to get everything, and then color coding the positions of cracks in that slab, let's say, so that you could localize any cracks positionally, if you see what I mean. So yeah, typically you're not just acquiring one waveform, you're acquiring multiples and turning it into an image. Here we've got the damping, which controls how wide the pulse you excite with. So you can change the shape of your ultrasonic echoes that way. And then we've got a gain here, which allows you basically a volume button to increase or decrease the amplitude of the echoes. Here's the ultrasonic transducer I'm using. It's a contact ultrasonic transducer. The one in the image I showed you was made to be immersed in water, which you often do, but in this case, we'll be applying the ultrasonic transducer directly to the material under study, which, the first thing I'm going to show you is the advantage of sampling rate. So the two banner specifications of a digitizer are its sampling rate and its resolution. And the sampling rate is important in ultrasonics to the extent that it allows us to determine the position in time of ultrasonic echoes. So here I've shown a typical ultrasonic echo. Yes, it's mathematically generated, but it could be a real ultrasonic echo, sampled at a relatively low speed on the bottom image. So what we've done here is satisfied what we call Nyquist criteria, which many of you may have heard of, which is a mathematical requirement that you must sample at least twice a signal's maximum frequency in order to follow that signal and not have its frequencies aliased or distorted to lower frequencies here. So we've respected the Nyquist criteria by sampling at least twice at exactly twice, in fact, the central frequency of that ultrasonic echo. And you can see on the bottom image, we do get a rough idea of what the echo looks like, but it's a pretty crummy view of the signal. Once we move up to 5 or even 10 times sampling, now we're sampling at 10 times the central frequency of the ultrasonic echo, we can see that we get a really proper view of the echo. So really, we recommend, in the case of ultrasonics, that you sample at about 10 times the central frequency of the ultrasonic transducer. You can see that by sampling faster, really the sampling interval, the width between the samples, determines how accurately you can measure the position of that echo, which is usually paramount in ultrasonic measurements. You can see in the bottom one, we're kind of lucky that the peak actually falls fairly close to that vertical dashed line, but it might have fallen as far away as a full sample away. And then on the top one, we get a much better view. So the sampling rate, or more precisely, the sampling interval, sets the scale of how accurately you can determine the position in time of an ultrasonic echo. So high sampling rate, the feature of high sampling rate, translates directly into the benefit of good echo localization in time. Here I'm going to show you so here what I've done is actually we're looking at the signal, the ultrasonic signal itself in yellow on channel 1, and the trigger signal, the trigger pulse, on channel 2. Normally I would connect that to the external trigger input, but since we weren't using the channel 2 anyway, I figured for illustration purposes, and you can see we're triggering on that external trigger pulse, and the ultrasonic echo always comes quite quickly afterwards. What we notice right away is that things are jittering around and the amplitude of the external trigger pulse is jumping up and down. That's no failing of the gauge card. That's actually a broken pulsar receiver. And what I did actually was, so here we're looking at the full sampling rate of 500 megasamples per second. We're only looking at about 2 or 3 microseconds worth of signal. So what I've done in order to understand this noise is to decrease the sampling rate and increased the number of points up from 8192 to 8 million. And by doing that, we've increased the acquisition time from a few microseconds to several hundred, to 100, I guess, or so milliseconds. So that's a time scale de-zooming factor of what, 10,000. And by doing that, what I've done here is put the cursors exactly 100 milliseconds apart, and then I've counted this variation in the amplitude of the external trigger pulse. And you can see there's exactly 12 cycles of this variation. 12 divided by 100 milliseconds works out to be at 120 hertz, which is exactly twice the 60 hertz line frequency. So that tells us that somehow our ultrasonic pulse receiver is picking up twice the line frequency. So almost that diagnoses what needs to be done to repair it, which of course we won't do. So now I've shown you what the raw ultrasonic Big Bang signal looks like when we don't have the transducer connected to anything. Here what I've done is connected it to a slab of aluminum, I think that is, and we put a little lip balm, really, any kind of grease basically, to couple the couple the transducer to the metal. And so that's the signals we're going to look at. Now, unfortunately, I haven't shown both the Big Bang echo and the back wall echo, but that's the back wall echo. You can see it's much smaller. It's not saturating the input the other way it is. So that's the echo. It's jumping around because of that 60 hertz noise we told you about. And that's the first thing we're going to get rid of. Oh, sorry. No, the first thing I'm going to do is, in this next one, is zoom in on this echo horizontally. So I'll stop here. Whoops, stop. And let's see. We're looking, so the output of the ultrasonic pulsar receiver is a plus and minus 1 volt output. So we have matched that to the Razor Plus's plus and minus 1 volt input range. And we've got Gauge Scope. I'm sorry, this is Gauge Scope, our flagship oscilloscope software that operates all of our gauge cards and allows you to operate the card without writing a line of computer code. Ultimately, most of our customers do end up programming the card themselves and integrating it into their own custom measurement system. But GaugeScope is a great platform to demonstrate the card and also get familiar with it and any troubleshooting necessary. So here we show that the vertical scale is 1 volt. So you can see the full scale input is plus or minus 1 division on this scale. What I'm going to do now, I'm going to start the video again, and we're going to zoom in on vertically by a factor of 100 to demonstrate. You see, if this were this is a 14-bit digitizer. If this were an 8-bit digitizer, then that would mean that there's 2 to the 8, which is 256 digitizer levels spread across this plus or minus 1 volt range. I should note that the vast majority, virtually all, not all, but almost all, oscilloscopes, standalone box oscilloscopes, are 8-bit devices. So most of them will have, as I say, 256 levels distributed across the input range. So what I'm going to do now is zoom in, zoom in by a factor of 100. You see over here, we're going to go from 1 volt vertical scale. We're going to go, cursor's going around there, 1, 2, 3, 1, 2, 3. Now we're down to 10 millivolts per division, which is 1/100th of what we were looking at before. That is, instead of a 1 division, plus or minus 1 division being full scale, plus or minus 1 division is now only 1% of full scale. And so each half of the range has half of the 256 levels across it, 128 levels. If you ignore the difference between 100 and 128, it turns out then this division height here is equal to 1 level on an 8-bit digitizer. So what that means is that if we were using an 8-bit digitizer, all of these subtle echoes here, the staircase would be 1 division high. So this one level high. So this echo, for example, which is about 2 divisions high, would just show as one would show as two staircases, if you see what I mean. And little subtle wiggles like this, which are below a division, would be lost completely if you were looking at an 8-bit digitizer. Because, however, this is a 14-bit digitizer, and the difference between 8 and 14 is 6. 2 to the 6 is 64. That means you have 64 times more levels. Okay, so for every division with our 14-bit digitizer here, we don't have just one level, but 64. And that allows us to follow these very subtle wiggles in the signal. So ultrasonic people generally do not have to be sold on the value of high resolution, you see, because the high resolution feature translates directly into the benefit of small echo detectability thresholds. And because, as we said before, that a flaw echo, flaws can be arbitrarily small, and the echoes from them can be arbitrarily small. Flaw echoes can be arbitrarily small. So the more resolution you have, the lower your minimum echo detectability threshold. So that's a real direct translation from a feature to a benefit. So now we've gone over the benefits of the two banner features of a digitizer, high sampling rate and high resolution, and shown how both of them are huge advantages in ultrasonics. Here's the same illustration done more on the blackboard. Here what we've done is calculated the minimum the best case back wall echo you could get for a slab of steel in water. Okay, here's the front wall echo, and because it's so big, you can't increase the gain. You remember I had that knob on my ultrasonic pulsar receiver. I can increase the gain of the amplifier, but I can't increase the gain any more than it already is here, because I would saturate this front wall echo. So I'm forced by the front wall echo to keep the gain at a certain amount. And that limits then, as I say, by the physics of the situation, the size of this back wall echo, which turns out to be only about 2 levels for an 8-bit digitizer. So this is the very best case of what you can get off a back wall echo of steel and water. I haven't accounted for attenuation in the steel or divergence of the beam, right? The beam spreads out. That also lowers the echo. So any other effect that I've left out that you can name will conspire to reduce this echo even further than it already is. It's already pretty darn small, but it'd be smaller still in real life. And then if we go to flaw echoes that can occur between these two echoes, those again can be arbitrarily small. So for steel and water, the very best case for an 8-bit digitizer is 2 levels, which stinks, I'm arguing. If we now look at a 14-bit digitizer, where we have, again, 2 to the 6, 64 times more levels, we can really get a good view of this echo. So that, again, illustrates the power of high resolution in ultrasonics. Now what? Okay, now we're going to look at scanning. Is that right? Sorry. Oh, no, I'm sorry. We're going to use the effect of this jitter from the 60 hertz here. So we've got the echo. There it is jumping all around. In gauge scope, I'm able to do signal averaging. That's where we take multiple waveforms, sum them all together, and divide by the number of waveforms in order to signal average. So the blue result there is the result of averaging together, I think it was 400 acquisitions of the single acquisitions of the yellow waveform. So you can see, and I'll run it again here, you can see that by doing 400 averages, we average away the jitter and the amplitude variations associated with the 60 hertz pickup to where it's completely gone. So this illustrates the power of signal averaging in ultrasonics. The downside is I can't move as fast because I'm not just taking one waveform per position, let's say. I have to take 400. That sort of illustrates a general principle that the longer I measure, the better measurement I get. This sort of translates into, the higher sampling speed you want, the less maximum resolution is available typically. Again, we'll go to the blackboard case of signal averaging. Here's, again, a simulated ultrasonic echo with various levels of random noise, not 60 cycle pickup. You can see at the bottom, just a one-shot acquisition of the ultrasonic echo. And there we can see we've got a signal-to-noise ratio of about 1. The echo is not much bigger than the noise level. But as we average successive waveforms, sum them together, we can reduce the noise because the noise tends to average to zero, whereas the ultrasonic echo is the same shape for every acquisition, and so it constructively interferes. And indeed, if we do 100 averages here, we can almost average the noise away completely. In fact, you can show that the residual noise will decrease as the square root of the number of averages. And here we've taken 100 averages, so we've reduced the noise by a factor of root 100 or 10 in that top image. Now, as I say, GaugeScope does averaging in software. Okay, so what it'll do to get 100 averages, it'll download 100 waveforms, sum them all together in software, and present the result. But what the gauge card is able to do, actually, with a special expert firmware option for signal averaging, is to actually sum the waveforms up on the card itself, okay, and thereby alleviate, well, it does two things. It alleviates the task of doing the averaging from the host computer, but more importantly, it dramatically reduces the data volume. Basically, you send the card 100 averages, instead of getting 100 waveforms, you only get one waveform. So now you only have to download one waveform instead of 100, and that can allow ultrasonic acquisition to go correspondingly faster. So by doing the averaging on board, we get two advantages. We free up the PC from doing the calculations. We also reduce the data volume, thereby increasing the overall throughput. So that's a very powerful feature of gauge cards, all of them really, not just the Razor Plus and RazorEdge, but all of them are equipped with onboard signal averaging. Now we're going to move to something a little more subtle, okay, and this is our trigger out feature, okay. All gauge cards are equipped with a trigger out functionality, which, as the name suggests, spits out a pulse, which you can see here in green, every time the card triggers. So you see we're now using a sine wave, not an ultrasonic signal, to trigger the card at the zero crossing here. The trigger point is this vertical dashed line. And I'll run it again here. And a couple of microseconds later, the card spits out this sharp pulse suitable for triggering. Now, I'll start with the secondary advantages of this, which are that basically normally, or the sort of conventional way to do ultrasonics is to have the pulse receiver externally trigger the gauge card. In this case, if we reverse the arrow of triggering and have the gauge card trigger the ultrasonic pulsar receiver, if in fact it is externally triggerable, which my low-end pulsar receiver was not, it is not able to be externally triggered, so it can't profit from this feature, but many of them can, most of them can. So by reversing the trigger arrow, instead of sitting around waiting for the next trigger when it comes, the card can actually generate the trigger itself as soon as it's ready. So that's kind of advantage number one. The second advantage is that although you can set up the card to process the triggers quickly enough that it shouldn't miss any trigger, I won't say you're never quite sure, because you can be, but here, because you're generating the triggers yourself, you're actually triggering the card from software, which makes it spit out the trigger out pulse, which triggers your ultrasonic pulse receiver. There's no possibility of missing triggers because you don't generate them until you're ready for them. So these, again, I say are secondary benefits of the trigger out functionality. The main advantage, however, in order to consider that, we have to understand the way the gauge card triggers. Some people think that when the external trigger arrives at the gauge card, it starts digitizing. That's not true. You actually start the card digitizing pre-trigger data, and it sits there waiting for the trigger. And when the trigger occurs, it sort of bookmarks that point as the trigger point, okay? And here's the key, somewhat subtle point, okay? If those triggers are asynchronous or unrelated to our 500 megasample per second, 500 megahertz sampling clock in this case, and why would they be? Why would they be related in any way? They aren't, of course. The boxes aren't connected anyway, so there's no reason. Since the triggers are asynchronous to the sampling clock, on successive acquisitions, they're going to arrive with different phases with respect to this trigger point. So here I've drawn 5 different black triggers, okay, that occur on different acquisitions, but those would all be logged as this trigger point, because that's the next sample point, that's the next clock edge after the trigger occurs. So basically, the card can't tell the difference between these 5 external triggers. When you then plot them on top of each other, the signal will appear to dance left and right by exactly 1 sample. We've had customers call up and say, what's the problem? The signal's dancing left and right by a sample. No, no, sir, this is no failing of the gauge card. This is a fundamental consequence of the asynchronicity between the clock and trigger. So how do you beat that asynchronicity? Well, by using our trigger output, which is synchronous. It's illustrated in red here. It always occurs. Its phase is always the same. It may not be exactly lined up with the trigger point. In fact, we know it comes out several samples later, several dozen samples later. But the point is, it's rock steady as compared to the phase of the sampling. So it doesn't have this 1-point jitter. And if we can trigger our ultrasonic pulsar receiver box with this trigger, we can the ultrasonic signal will inherit the synchronicity of the trigger out, and thereby also not have this 1-point jitter. So we're going to illustrate this actually with a sine wave. Oh, the same sine wave we had in the so here we had the sine wave, and then a few microseconds later, the trigger out pulse comes in. So if I zoom in on the sine wave, which I've done here into the 0 crossing, we can see it jitter back and forth. And if we use gauge scope's persistence function, which we're going to do in a sec here, which suppresses erasure doesn't allow erasing of the waveform between acquisitions, they build up, as you can see here. So it's going back and forth here and sweeping out this ribbon over time. And these 2 cursors here I've separated by exactly 2 nanoseconds, which is, 2 nanoseconds, yes, which is the sampling interval, okay? So the inverse of 500 megasamples per second, inverse of 500 megahertz or 500 megasamples per second is 2 nanoseconds per sample, okay? Every 2 nanoseconds we take a sample, and indeed this 2 nanoseconds, the division width is 10, so this spacing is 2 nanoseconds, is exactly, as we predicted on the previous slide, the width of that ribbon. So here we are showing the unbeatable 1 sample jitter that occurs for an asynchronous signal, because of course the sine wave from my generator knows absolutely nothing about the sampling clock from the gauge card. But if we shift to the right now, okay, over to the trigger out pulse, we can see there's a falling edge of the sine wave still jittering by 1 sample in yellow there, but the green trigger out pulse, I'm sorry, what I've done here is taken the trigger out pulse and looped it back into channel 2, which normally you wouldn't do. Normally you'd trigger out something else out, but I'm just trying to show the stability of it. So now we turn on the persistence again, and we get a width. So now I've gone down to 2 nanoseconds per division, and you can indeed see from the cragginess, right? You can see here that a sample is the difference between these 2 sharp corners here, right? That's where the lines are connected. So those are the points. So that proves basically that a sample is a division wide, but you can see that the width of the ribbon is way less than a sample. I'd say it's something like 1/20th of a sample. So we can see that the jitter, because of its synchronicity, the jitter on the trigger out pulse is not 1 sample, but something like a 20th of a sample, 20 times better. How often do you get a 20 times improvement factor in this life? Not often, I'll tell you that much. What was I going to say? That yes, this jitter is limited only by the electrical jitter of the components themselves on the card, okay, which is kind of unbeatable. But there's none of this 1 sample kind of jitter that otherwise occurs because of asynchronicity. So again, what we would do is connect this trigger out pulse to an externally triggerable pulsar receiver. It would inherit the synchronicity and the lack of jitter of the trigger out pulse, and you would have 20 times less jitter on your ultrasonic signal. And since, of course, you're trying to get the position of echoes, that correspondingly improves your echo localizability and therefore the quality of your ultrasonic measurements. So I sort of lied before I suggested that it was a slab of aluminum I had. In fact, the aluminum slab has these very special holes drilled in them. I was looking at a part where there were no holes before, but here we're going to in fact scan over these holes, but on the other side. So we've got a shallow hole, a medium hole, and a deep hole here. And you could imagine these were on the other side, the buried side of your reservoir, so you couldn't see them. We're going to go over, there's another view of the holes. We're going to scrub, I think they call it, over. So these holes are underneath the slab now in this direction I'm showing with my cursor. We're going to scan across this, scrub across this, and look at the position of the 3 echoes in gauge scope. So that's what we're doing here. So the transducer is not connected. We're going to put it down on the slab. There's the back wall echo with no holes. We move on. There's the shallow hole, you see? So there's almost as much metal. There's the medium hole, right? And then the very deep hole has very little metal to go through, so it bounces back right away, you see? So as I say, when the hole is shallow, then most of the metal is still there, and you hit, it's almost a map, right? You can turn this from time into distance, and indeed some ultrasonic systems will be calibrated in distance measurements. Right here, that told us that the first hole was shallow with an end here, and then with a deeper end on the medium hole, and a very deep end on the deep hole, if you see what I mean. So we did that manually. I scanned back and forth running gauge scope, but of course I didn't by any means capture all triggers, because in between each acquisition, gauge scope had to connect all these line segments. That probably took several milliseconds, and I can tell you there's several triggers coming per millisecond. So we missed, dozens and dozens of triggers in between each acquisition and display under gauge scope, which typically you don't want to do. You want to be able to scan as quickly as you can. So we're going to illustrate now the multiple record feature of gauge scope. So this gauge card I'm looking at has the gauge card I'm looking at has 4 gigasamples of onboard memory. Now we can use that continuously. We could trigger the card once and fill up the card's memory. The card's capturing at 500 megasamples per second. If we were on one channel, there's 2 bytes per sample, so it's actually sorry, I won't do that conversion. I'll just say it's capturing 500 megasamples per second. That's half a gigasample per second. So every gigasample would correspond to 2 seconds. We've got 4 gigasamples of memory, so we could capture continuously for 8 seconds. However, our ultrasonic signal is only active for a few microseconds every millisecond or so. So sort of 99.9% of the time, it's boring. It's a flat line. It's 0. And we don't want to waste our onboard memory by filling it up with 99.9% of the time with flat lines. So what gauge scope allows you to do is trigger the card, acquire a few microseconds worth, and then rearm the card lightning fast in hardware within a microsecond, and then wait for the next trigger to occur, thereby not filling the memory with all kinds of uninteresting data. So now, if we were only to capture a 0.1%, 1 in 1,000th, because we're capturing a few microseconds worth of data every millisecond or so, it's more like 99% of the time we're not acquiring. So our 8 seconds worth of acquisition would be multiplied by 100-fold, and we'd be able to acquire these triggers, not continuously, in a segmented fashion using our multiple record mode for something like 80 seconds. Well, I'm not going to do that. I just wanted to give you an idea of the power of this. So we're going to illustrate it. So what we did was we did an acquisition. Okay, I set up the pulsar receiver to create triggers at about 350 times per second, okay? And then I scraped across the 3 holes on the non-hole side with the ultrasonic transducer over about 3 or 4 seconds worth. and I acquired all those triggers in our multiple record mode. And now I'm going to look at them in gauge scope. So I'll open them. You'll see the colors are significantly more brilliant than they were in the screen capture I did. Assuming that's translated through the Teams or the whatever this telecon is called. So I'm going to turn off my live signals here, and I'm going to say File, Load Channel, Quick Access. It's this one. Okay, this one, and then up. It's under this one, right? Training, no, training, webinar, webinar, Razor Plus Edge. Here we go. So here's my multiple record file I acquired. Open. So you see, as I said, I acquired 1,000 waveforms over with a trigger rate of something like 350 hertz, 350 triggers per second. So as a result, I acquired for about 3 seconds. I scrubbed the transducer across those 3 holes in 3 seconds. So let me zoom in horizontally and vertically. And the first thing I want to show you is to prove to you that I'm really acquiring at that fast trigger rate. You recall that we proved that the oscillations on the signal that resulted from the 60 hertz or 120 hertz pickup were oscillating at 120, and since 120 hertz. And since we're acquiring 350 triggers per second, 350 hertz triggers, we should be acquiring about three of those. There should be about 3 acquisitions per 120 hertz cycle. So if I flip through these waveforms one by one, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. You can see 3, 1, 2, 3. You can see, as I predicted, the cycle of the waveform. We're actually seeing the 120 hertz oscillating because we're acquiring so quickly at 300. Well, actually, it's not as quickly as the gauge card can go, but it's pretty darn quick at 350 waveforms per second. We can actually see that oscillation. So that kind of proves we're acquiring them as fast as I thought I did. Now I will press play. Okay. So we have these, what I call the VCR buttons. For those of you who remember those archaic devices, I'll press play, and we ought to be able to see the same thing as we did before, really. But now we're capturing every single waveform at 300 waveforms per second. As I say, because the card's able to rearm itself in hardware after each acquisition, we can go at rates. The card can really go at rates of 10, 100 times faster, 10, 30, even 100,000 triggers per second. So there's the shallow hole. You see, we still see a bit of the back wall echo because the hole is smaller than the transducer, so you're still getting some reflections from the back wall of the slab, not from the hole. So there we're passing over the first hole. Now we're in between the 2 holes, so we only see the back wall echo. Then we'll see the medium hole, and that echo arrives sooner because there's less meat, less metal in between the wall and the hole. And we pass over it. See, it increases, starts to decrease again. Of course, we have to ignore the oscillations. And then how we doing? Okay, we're 70% of the way through. That was the trick. And I could have gone faster, but then we'd be here all afternoon. Or wanted to fit within the seminar time. So then we'll see the final echo, the shallow hole. We even get, as you can see, 2 reverberations there. We've got a second hole. A second echo, that's the sound bouncing off the hole, bouncing back off the front wall, and then off the hole again a second time. And as you see, we always get the back wall echo a bit because the hole is the area of the hole is smaller than the area of the transducer. So that's an illustration of our very powerful multiple record mode, which still operates in what we call memory mode. So for our final illustration here, we're going to show streaming. Okay. So for streaming, I'm going to use a sine wave signal from this generator, simple generator. I'm not an ultrasonic transducer. What I'm going to do during the acquisition is play with the amplitude knob. So we'll show you the acquisition, but I guess the acquisition takes how long? 20 seconds. 20 seconds. So what I did was I reduced the amplitude slowly, counting 1, 1,000, 2, 1,000, so then increased it slowly, then left it, and then quickly decrease, increase at the end. Okay, so you'll see that in our acquisition. So here's the actual acquisition going on. So gauge scope supports our memory mode acquisition, which has the disadvantage that it's limited to the card's onboard memory, which is pretty darn big, but it's still finite. So it's limited to acquisitions of that size. After you fill up the card's onboard memory, you have to stop and download it. But it's a simpler mode to operate in and operates under gauge scope. In streaming, you actually, so again, memory mode is where you capture the data into the card's onboard memory, stop and download the data, during which time you're blind, and then you can repeat that process. So you're always missing data in the memory mode. In streaming mode, however, you actually fill the card's onboard memory, but empty it as the acquisition is going on. The memory is configured as dual port, meaning it can be written to and read from at the same time. So by doing that, assuming that the memory is not being filled too quickly and that it's being emptied quickly enough, and this is where the consumer of the data has to hold up his end of the deal. He has to consume the data quickly enough that all the data are consumed, that there's no overflow, which occurs if the consumer doesn't consume quick enough. Okay, so what is the consumer? Well, often the consumer is our SSD drives, solid state drives. You can get many terabytes of fast solid state drives these days. So we've configured, and Gerald's the expert in that domain, configured recording systems that are able to record for many hours and even days with, as I say, in some cases, hundreds. I guess we can put up to 200 terabytes of solid state storage drive in the computer. However, we have to construct the disk system such that it's able to take the speed of the acquisition. Another popular target is a GPU card, where you can stream data to the GPU card and have the GPU card perform operations processing the data and hopefully also reducing it. Okay, so that's another popular target. Here, what we're going to use is PC RAM. Now, the disadvantage of PC RAM is it's relatively limited. You can get up to something like a terabyte of PC RAM, maybe more these days. But the advantage of PC RAM is it's real fast. So we don't have to worry about PC RAM holding up its end of the deal and being able to consume the data stream quickly enough so that there's no loss of data. So to do this, we've enlisted our C sample program, Gauge Stream to RAM. As you can see here, let me zoom in on this somewhat. It's a console application, meaning it doesn't have a GUI associated with it. All our sample programs are structured this way to keep them as absolutely simple as possible, so that the customer who's going to build upon the sample program doesn't have to disentangle the GUI elements from the acquisition elements. So virtually all of our sample programs simply do one acquisition, store the results to file, and that's it. Okay, so we run the sample program, and this almost becomes like by streaming into RAM, it's almost like you're replacing the card's onboard memory with PC RAM. So you can really, conceptually it's very similar. You see what I mean? So first thing the sample program does is report back the board name, selects the expert streaming image, which is a separate functionality that has to be added to the card. And it's set up a buffer, okay, a buffer in the PC RAM of, this is 20 billion bytes, 20 gigabytes. Because there's 2 bytes per sample, that corresponds to 10 gigasamples. Because we're acquiring at 500 megasamples per second, every 2 seconds, we acquire a gigasample of data. So since we're going to acquire 10 gigasamples, 10 times 2 is 20, we're going to acquire 20 seconds worth of continuous data. Now, you may recall before I said if we filled up the card's onboard memory of 4 gigasamples, that would take 8 seconds. So we've increased the memory capacity of the card by 2.5, going from 4 to 20 gigasamples, sorry, 4 to 10 gigasamples, or from 8 to 20 seconds of acquisition. Okay, now this computer only had, as I say, something, I think it had 32 gigabytes of RAM in it, which is fairly small. I was able to usurp or appropriate 20 gigabytes worth. As I say, you could put up to a terabyte or more, thereby 50 tupling the amount of memory in the computer, and bring it from, or the amount of memory you can use for the acquisition, thereby going from 8 to 8 times 50. What would that be? 400 seconds. Okay, so we could capture up to 400 seconds just with PC RAM. So the RAM buffer is allocated, initializing the RAM buffer, and then we start the streaming acquisition. So unfortunately, I couldn't record this with my screen recording software. This amount here increases as the acquisition goes on. So here's the final amount, which is 20 gigabytes of data acquired. Here's the rate. Okay. Now the rate from the card is 500 megasamples per second on one channel times 2 bytes per sample is 1 gigabyte per second. Okay. So here we're not. That would be 1,000 megabytes per second, but there's kind of an overhead time at the beginning. So as you watch this rate, it starts out low and gradually increases sort of asymptotically to the real value of 1,000. But we know we haven't missed any data during the acquisition because we didn't see any FIFO overflows, okay? So the FIFO being the onboard CompuScope memory through which the data are streaming. So we're streaming the data onto the PCI bus and into PC RAM, but through the card's onboard memory. So if the PC RAM were for some reason, which it never does, to get locked up and not for a little while, or if the PCI bus was to get locked up, which can happen, but not for very long, the card's onboard memory would sort of accept for that overflow, just as if you plugged a plug in the sink and kept the water flowing. It wouldn't overflow until the sink got filled up. Similarly, until the onboard memory got filled up, you wouldn't miss any data. And if the plug got pulled in the sink, and I'm jumping from one analogy to the next, as long as you pulled the plug quickly enough, the water that was filled up in the sink would drain off. Similarly, if as soon as the PCI bus became unlocked, it would empty out that FIFO as long as it wasn't blocked for too long. So that analogy works quite well. So as I say, because we didn't see any FIFO overflows, we know we haven't missed any data. And indeed, we've also examined the data to make sure there's no breaks in the sine waves we acquire. Here we can see the elapsed time was 22 seconds. The actual acquisition was only 20 seconds, but there was a kind of a 2-second setup time. It tells us the stream was successfully finished in one segment. And again, no FIFO overflows. And then the total data, again, 10 gigabytes. And then we save to disk, which actually takes significantly longer than 20 seconds because the disk wasn't, it's nothing special disk basically, and so isn't able to take that rate of 1 gigabyte per second. I should add that that our gauge cards can go at up to 5 times faster than 1 gigabyte per second, up to 5 gigabytes per second. These particular cards we're talking about can't generate more data than that. So basically, for the Razor Plus and the RazorEdge card, there's no rate at which you can't stream. So now that we've acquired this data, it's in this file called amp twiddle because I twiddled the amplitude. As I said, increased it slowly, decreased it, and then, other way, decrease, increase, and then quick decrease, increase. Again, we've got our exactly 20 gigabytes file with 128 byte padding, probably required for file size rectification or whatever. So what we're going to do now is open up this file in our gauge viewer here. So here, our gauge viewer. So there's the sine wave. We're going to scan through. So each gigabyte you'll see is 2 seconds. So here you can see it started to decrease its amplitude, coming up on 2 seconds, 1 gig, 4 seconds now. We're getting to the lowest point there. 6 seconds, almost no signal. Then I start increasing the amplitude again. 8 seconds, 4 gigasamples. 10 seconds, 12, 14, 16, and then quick reduction increase. So here you can see we've acquired at a very high rate of 500 megasamples per second, looking at a pretty fast sine wave, but we're able to track it over human type timescales, in this case 20 seconds. So that's an illustration of our streaming functionality available on all our CompuScope cards with sample programs illustrating operation in different streaming modes. So with that, I will pass the talking stick back to Gerald and stop sharing, right?
All right, thanks, Andrew. While we have highlighted the RazorEdge and Razor Plus, Gauge does have more digitizer models to choose from. And here's a table matrix of our current digitizer product models. You can see this when you get the copy of the presentation, but it kind of goes through the various specs of the different models, their starting at pricing and so forth. And as we previously indicated before, all of our digitizers come with the GaugeScope Lite Edition software and our complete library of SDKs at no additional charge. Andrew mentioned we do have the capability of adding digital signal processing, whether it be with the onboard FPGA on the digitizers or streaming to GPU CUDA cards. As he mentioned, we can use expert streaming to stream to a GPU target card or to the host CPU for processing analysis or to high-speed storage for signal recording operations. Or we can use various expert FFT features depending on the digitizer model. All of our digitizers are strongly supported with our software. In addition to the GaugeScope and SDKs we mentioned, we also have an IF signal recording app called DSScope, which basically adds the additional capability of conducting high-speed signal recordings to your system with the ability to view that data snapshots in real time as the data is being recorded on multiple analysis displays. Similarly, we have an RF signal recording based application called Spectroscope RT, which is very similar to DSScope. It just adds the additional RF front end support for RF receivers that will down convert a high frequency signal down to a lower IF range that our digitizers can accept to then do the real-time signal recordings to storage. We also offer optional SIG-stations for complete turnkey systems. These are high-performance PC workstations that are designed for integrating our Gauge cards and really for maximizing their operational performance. For real-time operations, it's typically critical that the underlying host platform is capable of sustaining high-speed PCI Express data streaming rates, especially to and from multiple instruments that are operating together simultaneously. So the SIG-stations come with all the Gauge cards, features, and software fully tested and installed so that the user can be up and running with their system solution right out of the box, and thus saving time and minimizing risks of self-integrated systems. Our custom configurations can be portable, laptop, desktop, 1U, 2U, and 4U rack mounts, and we can have storage capacities of high speed up to all the way up to 368 terabytes currently today. So at this point, we're now open for any questions that anyone may have. We can provide tailored custom hardware and software solutions to meet specific application requirements. You can review our products in more detail on the web at vitrek.com/gauge, or email us at sales-gauge@vitrek.com, or call us toll-free at 800-567-GAUGE, or for outside North America, 815-838-0005. Thank you very much for your time today. We hope you enjoyed this presentation.